Hi, welcome to Chapter 17, Overview Part 2, where we're going to talk about acid-base titrations. So what is a titration? Well, this is a technique where you can have an acid or a base solution of a known concentration, which we call the titrant, and you are slowly adding it to a base or an acid of an unknown concentration. And you could have an indicator, which is shown in this picture here. Indicators change colors. Or you could use a pH meter to measure the pH as you're dripping one into the other. And when your solution reaches the equivalence point, the amount of acid will equal the amount of base. And so your stoichiometric amount of the acid equals that of the base. So what happens when we titrate a strong acid with a strong base? From the start of the titration to the near part of so this part of the graph right here we're talking about, your pH is going to go up very slowly. Then you're going to reach this area here where your pH is rapidly changing. And right here in the middle is your equivalence point. And then you're going to get to this region here where the pH again now changes slowly. For a strong acid and a strong base, your equivalence point is at a pH of 7. So let's talk about each of these regions. So let's start down here. Again, we're titrating a strong acid and a strong base. From the start of the titration to near the equivalence point, your pH is changing very slowly. And why is that? So what species are in significant concentrations at the beginning of this titration curve? At the beginning of the titration curve, you have just your strong acid, so you have a lot of hydronium in there. And then you're dripping the base in there. So what happens is the hydronium is slowly getting neutralized by the hydroxide that you're dripping into the solution. And that is why the pH is slowly increasing, because you are slowly neutralizing some of these H's that are floating around in here. So what species are affecting the pH of the solution? Well, the hydronium concentration from the acid is reacting with the OH from the base, so it's neutralizing it. So you're going to have less hydronium in there, so your pH will increase. But there still is quite a bit of H plus in there, which is why the pH is not changing drastically. Now, what happens just before and after the equivalence point? So we're here to here. So what species are in significant concentrations at this point? Well, before, right here, you're going to have water, your spectator ions, and just a few H pluses. After, you're going to have water, your spectator ions, and a few OH minuses. Right in the middle, your H plus will equal your OH minus. So what species are affecting the pH here? Well, below the equivalence point, the H plus from the acid is changing the pH. Above the equivalence point, it's the hydroxide from the base. Now, this drastically changes is because you have such a small concentration of hydronium right now that just by adding a little bit of a base, it will drastically change the pH. So now we're going to talk about the equivalence point, which is right here. At the equivalence point, the moles of your acid must equal the moles of your base. And at this point, your solution is only going to contain water and the salts from the cations of the base and the anion of the acid. Again, this is for a strong acid and a strong base. So what species are in significant concentration at this point? You're only going to have your spectator ions and water. What is happening at this point? The moles of your acid must equal the moles of your base. And for a strong acid and a strong base, the equivalence point occurs at a pH of 7. Now what happens after we pass the equivalence point and we're in this region here? So as more base is added, this will increase the pH again, and it's increasing it kind of slowly here because you have so much OH in there now. So what species are affecting it? Well, you have, in this part you have OH, you have spectator ions, and you have water. What is happening at this point? The OH concentration is increasing, so the pH is increasing. Why is the OH concentration increasing? It's because you are continuing to add the base. Now, what happens if we start with a strong base and we titrate it with a strong acid? The curve will look very similar to the previous one, except it's flipped over. You're going to start at a high pH because you're a base, and you're going to end at a low pH. Notice the equivalence point is still at 7 because we have a strong base and a strong acid. If you have two strong things mixing, the equivalence point will always be at a pH of 7. Now, what happens when we have a weak acid titrated with a strong base? So here we have our curve from the previous slide, strong acid and a strong base. Here we have a weak acid and a strong base. So what do you notice is different? Well, first of all, this starts at a pH around 1. And this is starting at a pH in between 2 and 3. So I don't know, let's say 2.5. So the starting pH is higher for the weak acid. And the equivalence point here is 7. And the equivalence point here is, I don't know, looks like 8.5-ish. So the equivalence point is greater than 7 here. So let's see why. So again, you have your weak acid, and you're dripping a strong base into it. So unlike the previous case, the conjugate base of the acid is important. It affects the pH. At the equivalence point, because you have this conjugate base present, your pH is going to be more basic, so it'll be greater than 7. In this type of titration, phenolphthalein is commonly used as an indicator because it changes color in this range here. You want your indicator to change color in the range where your equivalence point is. So here it's breaking it up into the sections. So what do we have to do here? So we're going to use Ka to find our initial pH. Then this region here is called the buffer region. And you're going to use stoichiometry and the Henderson-Hasselbalch equation to solve for pH in this region here. Interestingly enough, if you go to halfway to the equivalence point, so here the equivalence point is at 50, so if you go to 25 and you read off this value here, that will be your pKa value. So that's called your half equivalence. As more base is added, the pH is going to level off up here again. Same as the strong acid titration. So, what is really going on when we titrate a weak acid with a strong base? What two species are equal once the titration is halfway to its equivalence point? So we're talking about halfway to its equivalence point again. So we're here. What two species are equivalent? Well, at the equivalence point, all of the weak acid is neutralized and converted to its conjugate base. So the number of moles of your H plus must equal your number of moles of your OH minus. So actually, I should have crossed out halfway. What two species are equal once you reach the equivalence point? That's what this question is answering. So at the equivalence point, your moles of your H plus is equal to your moles of your OH minus. However, the pH is not equal to 7 here because the conjugate base from your weak acid makes your solution slightly basic. Okay, now let's talk about the half equivalence point here. What can you use the pH at the half equivalence point to determine about the acid? Well, at the half equivalence point, your pH is equal to your pKa. So you could use it to calculate your Ka for your acid. So at the equivalence point, when half of the weak acid has been neutralized, that means the concentration of your weak acid is equal to your concentration of your weak base. Therefore, pH is equal to pKa. This is why we can choose a buffer system by choosing a weak acid that has a pKa close to the pH that we're looking for. So here is a flow chart to show you how to do some calculations. So you're calculating the moles of your weak acid and then the moles of your base added. And this moles of your base will really be the moles of your anion formed. You're going to subtract it from the moles of acid to see how much acid is left. And then you're going to use Henderson-Hasselbalch equation to find the pH. Okay. I also have a step-by-step breakdown on how to calculate the pHs for a weak acid being titrated with a strong base in Schoology. So ways that a weak acid titration differs from a strong acid titration. A solution of a weak acid has a higher initial pH than a strong acid. So you notice, and what happens as your Ka changes here? So your initial pH will increase as Ka decreases. So as Ka decreases, your pH will increase. If Ka is decreasing, you are getting weaker, right? You have a weaker acid. So the weaker your acid, the higher your starting pH. The pH change near the equivalence point, so you notice here what's happening, is smaller for a weaker acid. So if you look, as I'm going up, my Ka is getting smaller, so my acids are getting weaker. Look at the blue curve. Look at the length of this region here compared to, say, the red curve. And notice this length is much smaller than, say, the red curve. So as your acid gets weaker, this change will get shorter. And the pH at the equivalence point will be greater than 7 for a weak acid. So here we have a comparison. The red curve is a strong base titrated with a strong acid. The blue curve is a weak base titrated with a strong acid. They both end at the same point, but you notice the starting pH is lower for a weak base. So the pH at the equivalence point in this titration is less than 7. So if you are titrating a weak base with a strong acid, your equivalence point will be at a pH less than 7. And in this case, you would use methyl red as your indicator. How do you know which indicator to use? Indicators are weak acids that have a different color than their conjugate bases. So once they go from acidic to base, they change their color. And each indicator has a certain pH range in which the color will change. So you want to pick your indicator that will change colors near your equivalence point. So an indicator can be used to find the equivalence point in a titration as long as its color change is in the region where the pH rapidly changes. So your color change has to be in this rapidly changing and near the equivalence point. And your indicator choice can be very critical. So here we have a base getting titrated with an acid. And this indicator would be a poor choice because notice it changes color before you reach this steep region here. So in this case, you would want to use methyl red because it's changing color right in the steep region and right near the equivalence point. What happens if you have a polyproduct acid? Remember, that's an acid that can lose more than one proton. So it has more than one H. When you titrate it, you're actually going to get kind of like two little titration curves here. So when a polyproduct acid is titrated with a base, there is an equivalence point for each dissociation. So here we have 2 dissociations, and you have an equivalence point for each one. You could use the Henderson-Hasselbalch equation, and you can see that halfway to each of these, so here and here, would be your pKa for that dissociation step. So let's do a practice problem. So here it's asking you to calculate the pH of a solution formed when you have 45.0 milliliters of 0.1 molar NaOH is added to 50 milliliters of 0.1 molar acetic acid. And this is the Ka value. We use acetic acid a lot, so by now you might have Ka memorized. Okay, so let's write the reaction that's occurring here. So this sodium hydroxide is going to dissociate. So whatever concentration your sodium hydroxide is, that is the concentration of your hydroxide. So our reaction, I'm going to leave the sodium ion out because that's a spectator ion. So you have hydroxide plus your acetic acid will yield water plus acetate. Okay, now what we need to do is calculate the concentration of hydroxide. So in order to, why are we calculating it when, oh look, it's right here. Well, no, we're adding it to our acetic acid, so the volume is changing. Okay, so you have to take your concentration, your original concentration of your hydroxide, times its volume, but in liters, divided by the new volume. So when you add these two together, and that's going to give you so that is your concentration of hydroxide. So you need to do the same thing for acetic acid. So you're going to take its concentration times its volume in liters divided by the new volume. And that'll give you molar of acetic acid. So now we're going to set up our ice table. So we have our acetic acid, our hydroxide, and our acetate. So our initial concentrations that we just calculated, we're going to write in here. So now what we have to decide is which one is limiting us. So our reaction here is 1 to 1. So whichever one is smaller is limiting us. So hydroxide is limiting us. So we're going to subtract the amount of hydroxide from both reactants and add it to our products. And then sum that up. Okay, so now we have the concentration of our base and the concentration of our acid. So now we can use the Henderson-Hasselbalch relationship. So that gives us, when we take the negative log of Ka, we're going to get 4.74 plus the log of our concentration of our base over our acid. And we're going to get 5.70 as our pH. You could have also used this and used our Ka relationship, right? And solved for, you could have solved it that way. This is the easier way. All right, let's try this problem now. So now it's asking me to calculate the pH at the equivalence point. In the titration of 50 milliliters of 0.1 acetic acid with 0.1 sodium hydroxide. If it's at the equivalence point and their concentrations are the same, that must mean the volume that we added of sodium hydroxide must be the same as the volume of our acetic acid. So if we calculate our new concentrations like we did in the previous one, you take your volume of your solution times your concentration divided by the new volume. And let's do acetic acid. What do you notice immediately about your concentrations? They are the same, right? And we're at the equivalence point, so they have the same amount of moles. And if they have the same volume, then their concentration is going to be the same. So what do we do now? Well, we know that because this is a weak acid being titrated with a strong base, at the equivalence point, our solution is going to be slightly basic, right? So what we have to do is get Kb from our Ka. So and when you do that, you get 5.6 times 10 to the minus 10. Because what's happening? You have some spare acetate ions in your solution, and they're going to react with the water, and they're going to make acetic acid plus hydroxide. So we want to figure out the concentration of this hydroxide. So we need Kb because that would be the concentration of acetic acid times hydroxide over our concentration of our acetate ion. Okay? So we could do our ice table where we have our acetate ion, our acetic acid, and our hydroxide. So now we're starting with 0.0500 molar, 0 of each. So minus x plus x, this should look familiar. We've done this a lot, right? So now if we plug that into here, we get x times x. We could assume this is small, divided by 0.05 is equal to my Kb value. So then solving for x, which is the hydroxide concentration, we get that it is 5.3 times 10 to the minus 6. So if we want the pH, we're going to do 14 minus the negative log of this number, where this is just this term right here is the pOH. And when we plug all that in, we're going to get 8.72, which is slightly basic. So what are the major points, if your head isn't spinning? The equivalence point is where the moles of your acid must equal the moles of your base. The pH at the equivalence point depends on what you are mixing. If you have a strong acid and a strong base combo, your pH at the equivalence point will be 7. If you have a weak acid and a strong base combo, your pH will be slightly basic, so it will be greater than 7. If you have a weak base with a strong acid, then your pH is going to be less than 7. The strong acid is going to dominate. The endpoint is where your indicator will change colors, and your acid-base indicator, they are acids themselves, and you want to pick ones that the color changes in a range where the pH of the solution is equal to the pKa of the indicator. When doing calculations, you want to assume that strong and weak reactions go to completion. Okay? And that is the end of part 2.